Hello and welcome to Algebra 1, Lesson 9. In this video, we're going to continue to look at applications of linear equations. So in the last lesson, we started talking about word problems. And we talked about how you would go about solving a word problem. So the first thing you always want to do, you want to read the problem carefully and determine what you are asked to find. So generally, you might highlight that or write down, hey, this is what I'm looking for. That allows you to have a laser focus throughout your problem. The next thing you want to do is assign a variable to represent the unknown. Now, in a lot of these problems, you're going to have more than one unknown. So you're going to assign a variable to represent one of the unknowns, and then you're going to represent the other unknowns in terms of this variable. All right, the next thing you're going to do is write out an equation. And you're going to do that by reading through the problem. You'll have something equal to something else. This is going to allow you to write an equation, then solve the equation, and then state the answer in terms of the problem. So that's very important. You don't just solve the equation with a word problem and then hand in your paper and say, I'm done. You have to state the answer in terms of the problem. And then lastly, you want to check the result and make sure it is reasonable. If you get asked for how many cars are on a bridge and you get an answer that's -7, you probably got the wrong answer. Right? You should have either 0 or some positive amount in that scenario. So you want to make sure that your answer is reasonable. All right, so we're going to start out today by talking about everybody's favorite, which you will come to know them as mixture problems. So these problems involve mixing two or more substances and then finding some unknown. Now, the problems we're going to look at today are going to be relatively simple, but as we move forward, they're going to get more and more complex. So the first thing we need to understand with a mixture problem is how to find the pure amount of a substance in a mixture. So here's a quick example. So a chemist has 20 liters of a 25% acid solution. So what does that mean when I say a 25% acid solution? It means that 25% of it is acid. How much pure acid is in this solution? So to figure this out, you just take the amount of the solution, which is 20 liters. So I'm just going to write 20. I don't need to write liters there. And I would multiply it by the percentage of acid that's in it. So if it's a 25% acid solution, 25% of it is acid. Now I'm going to convert 25% to a decimal. So that's 0.25. And this will tell me how much pure acid is in the solution. So 20 times 0.25 is the same as 20 times 1/4. And I can do that in my head. That's going to be 5. Right, it's basically like taking 20 and dividing by 4. So there would be 5 liters of pure acid. It's 20 liters of a 25% acid solution. So how much pure acid is in the solution? Again, 25% of 20 is 5. So that means there's 5 liters of pure acid. All right, we're going to look at another one that's simple and kind of gives us a little warm up as far as, understanding how to find the pure amount of something. Okay, very, very important. So this won't be a typical mixture problem. This will be a very easy one. So for her birthday party, Tina mixed together 2 liters of Joe's fruit punch and 10 liters of Babe's fruit punch. Joe's fruit punch contains 15% fruit juice, while Babe's contains 45%. What is the percentage of fruit juice in the mixture? So what is the percentage of fruit juice in the mixture? How do I obtain that? Forget about the numbers for now. If I want the percentage of something, well, I would want the amount that I'm looking for as a pure amount over the total. So in this particular case, we're looking for the amount of pure fruit juice. So the amount of pure fruit juice, and that's going to be in liters, right? Because we're talking about this mixtures in terms of liters, over just the amount of the mixture. The amount of the mixture. And we know that this amount here, the amount of the mixture, is larger, and this amount is smaller. So we're going to end up with something that's less than 1, greater than 0, right? It's going to be a decimal, something like point something. Now I would then take that amount and I would convert it to a percentage, and then I could say, hey, this is the percentage of fruit juice in this mixture. So let's fill in the information here. How much pure fruit juice do we have? Well, we have 2 liters of Joe's fruit punch and 10 liters of Babe's. So we have 2 liters. This is Joe's. And we have 10 liters of Babe's. Now I can already figure out what the total amount of the mixture is going to be because 2 liters plus 10 liters is 12 liters. So I'm just going to write 12. Now, what's the concentration of each? Well, it says that Joe's fruit punch is 15% fruit juice and Babe's is 45%. So Joe's is 15%, and Babe's is 45%. So if I multiply 2, which is the number of liters of Joe's, times 15% or 0.15 in decimal form, that would give me the amount of pure fruit juice in Joe's fruit punch, right? The amount I added from that. So 2 times 0.15 is 0.3. Then if I do the same thing over here, if I have 10, which is the number of liters from the Babe's fruit punch, times 0.45, which is 45% as a decimal, that's going to give me the amount of pure fruit juice that I'm throwing in from Babe's fruit punch. So this is going to be 4.5. So if I sum these two amounts together, the amount of pure fruit juice that I'm putting in from Joe's plus the amount of pure fruit juice that I'm putting in from Babe's, I'd get 4.8, right? 0.3 plus 4.5 is 4.8. So essentially I have 4.8 divided by 12. So let's erase this real quick. We'll do our calculation. So again, what I figured out was the amount of pure fruit juice. I have 4.8 liters. And I know the amount of the mixture, that's 12 liters. If I divide one by the other, I'm going to get as a decimal 0.4. So as a percentage, I just move this guy over 2 places to the right, and I'd have 40%. So that means that my mixture is going to be 40% fruit juice. So I can come back up here. What is the percentage of fruit juice in the mixture? The mixture is 40% fruit juice. And it's kind of easy to check that. I mean, this is a very simple one. So Tina mixed 2 liters of Joe's fruit punch and 10 liters of Babe's fruit punch. Again, 2 plus 10 is 12. So that's the total amount of the mixture. Now, Joe's fruit punch contains 15% fruit juice. So if I take 2 liters, or just the number 2, and I multiply it by 15%, or in decimal form, 0.15, that means that I have 0.3 liters of pure fruit juice that's coming from Joe's fruit punch. Now, from Babe's fruit punch, I've got 10 liters, and it's 45% fruit juice. So I'm getting 4.5 liters of pure fruit juice there. Combine these two together through addition, and what I'd have is I'd have 4.8 liters of pure fruit juice in the mixture that is a total of 12 liters. So all you'd have to do is take 4.8 and divide it by 12, which is the total number of liters in the mixture. That gives me 0.4, and so as a percentage, that's 40. So 40% of this mixture is going to be pure fruit juice. All right, so let's take a look at a harder one now, one that's going to involve the use of variables to solve. So a metallurgist needs to make 10 milligrams of an alloy containing 82% silver. So let's stop for a second. Some of you don't know what an alloy is. So an alloy is a metal that's made by combining 2 or more metallic elements. All right, so then she is going to melt and combine one metal that is 28% silver. Let me highlight that, 28% silver, with another that is 88% silver. How much of each should she use? So here's our question. How much of each should she use? Meaning, how much in terms of milligrams should she use of the one metal that's 28% silver? How much in terms of milligrams should she use of the other metal that is 88% silver? So when we move to our next step and we want to assign a variable to represent the unknown, we have those two unknowns. So let's let x equal one of those. So let's let it equal, let's let x equal the amount of metal in milligrams that is 28% silver. Okay, so the amount of metal in milligrams that is 28% silver. Now, to express the other unknown in terms of x, you kind of have to read through the problem. This is a little tricky the first time, so I have to kind of walk you through it. Here's the information that you might have missed. A metallurgist needs to make 10 milligrams of an alloy containing 82% silver. This is the first key, 10 milligrams. So we know that X is the amount of metal in milligrams that is 28% silver. So whatever X is, if I add the other amount to it, the sum should be 10, right, in terms of milligrams, right? It should be 10 milligrams. X milligrams plus some other amount of milligrams should equal 10 milligrams. So now I can kind of work backwards and say, okay, well, 10 is equal to X plus this amount here can only be 10 minus whatever X is. And I know that's a little tricky at first, but 10 minus whatever this is, let's say X was 4, for example. I'm not saying that's the answer, but let's just say X was 4. So if this was 4, 10 minus 4 would be 6. So 4 plus 6 would be 10. In other words, whatever X is, the other amount, when added to that, has to sum to 10. So that's why this would work out. So if, let's say, X was 8, then this amount would have to end up being 2, right? Because these two amounts have to sum to 10. So that's where you're going to get this formula from. So X plus 10 minus X is going to equal 10. Now, that gives us our relationship for the other metal. So we could say then 10 minus X is going to be the amount of metal in milligrams that is 88% silver. And again, I know the first time you see that it's a little confusing, but as you work through these problems, that's going to become something you look for all the time. All right, so now we want to set up an equation. So some of you might immediately make the mistake and say, okay, well, I know the weights. So my equation is X plus 10 minus X equals 10. You might say, okay, let's go through and solve this. X minus X is 0, and then I have 10 equals 10. And you might go, okay, what happened? What's wrong here? Well, you don't have enough information. What you need here is to relate the fact that, okay, you have a certain weight for X, but that weight is a certain percentage of silver. So if 0.28, right, 28% as a decimal is 0.28, times X is used to represent the amount in milligrams of pure silver. Then we add this to, now we have the amount of metal in milligrams that's 88% silver. So 0.88, which is 88% as a decimal, times this, remember to use this parentheses here, 10 minus X, very important. Okay, you can't just put it next to the 10, that won't work. This is the same thing, it's the amount in milligrams of pure silver. So these two amounts have to be equal to what it told us in the problem. And in the problem, it says that the metallurgist needs to make 10 milligrams of an alloy containing 82% silver. So 10 is the total weight, and the percentage is 82%, so 0.82. And so now we have an equation. Now we have something we can solve. So amount in milligrams of pure silver is equal to the amount in milligrams of pure silver. One side is going to be equal to the other, and we have something we can work with. Let's go ahead and solve the equation now. So we'll have 0.28x plus 0.88 times 10. I'm just going to move this one place to the right, so that would be 8.8. Then minus 0.88 times x is 0.88x. Then equals 0.82 times 10 is 8.2. So if we combine like terms here, 0.28x minus 0.88x is going to give me negative 0.6x. Then plus 8.8 equals 8.2. I'm going to subtract 8.8 away from each side of the equation. That's gone. I'm going to have negative 0.6x is equal to 8.2 minus 8.8 is going to be negative 0.6. Divide both sides of the equation by negative 0.6, the coefficient of x. That's going to cancel with that. And this is going to cancel out also and become 1. So we have x equals 1. All right, so let's make sense of this. Remember that x is the amount of metal in milligrams that is 28% silver. So that we said was 1, because x was equal to 1 when we solved our equation. So we're going to say that she needs 1 milligram of the metal that is 28% silver. And then along with 10, which is the total weight of this thing, minus 1, which is the weight of the metal that is 28% silver, so 9. So along with 9 milligrams, remember we set that up as 10 minus x. 10 minus 1 would be 9. So along with 9 milligrams of the metal that is 88% silver. So that's what she's going to use to make this alloy that is 10 milligrams and 82% silver. So check everything out. If you go back up, again, a metallurgist needs to make 10 milligrams of an alloy containing 82% silver. So we know that 1 milligram plus 9 milligrams is 10 milligrams, so that part checks out. We just need to check the pure amount of silver in the substance. So our goal is to have 82%. Right? It needs to be 82%. So if we have 1 milligram, that's 28% silver, so times 0.28, and we add that to 9 milligrams, that's 88% silver, so times 0.88. This should be equal to 10 milligrams times 0.82. Right? And this is the exact equation that we set up. We just didn't know the values. So 1 times 0.28 is 0.28. And then plus, we have 9 times 0.88. That's 7.92. And again, 10 times 0.82 would be 8.2. So this is what I'm looking for. I'm looking for 8.2 milligrams of silver, right, in this 10 milligram alloy. So what is 0.28 plus 7.92? Well, that is 8.2, right? You get 8.2 equals 8.2. And so your answer here is correct, right? She needs to use 1 milligram of the metal that is 28% silver. She's going to have 0.28 milligrams of silver from that. And then along with 9 milligrams of the metal that is 88% silver, she's going to get 7.92 milligrams of pure silver from that. She combines them together, and she gets 8.2 milligrams of pure silver for her alloy that is 82% silver. Right? It's 8.2 milligrams out of a total of 10 milligrams. All right, so now we're going to talk a little bit about something known as motion problems. These problems involve the distance formula, and there's more than one distance formula. We're going to cover the other one in the last part of Algebra 1. It relates to how much distance is between 2 points on a graph. We're not talking about that one. We're talking about distance equals rate times time. So rate of speed times the amount of time traveled at that speed. And this formula is very, very intuitive. Pretty much everybody has taken a road trip at some point and said, if we go 60 miles per hour for 3 hours, we're going to end up going 180 miles. So in other words, if my rate of speed is 60 miles per hour, and this is in terms of hours, so our time has to be given in terms of hours for this to make sense. So 60 miles per hour times 3 hours, how far are we going to go? Well, forget about the units here. We're going 60 times 3, that's 180. So we're going to end up going 180 miles, right? If I go 60 miles per hour for 3 hours, we go 180 miles. We all know that. And that's what the distance formula does. It tells us that the amount of distance traveled is equal to the rate of speed times the amount of time traveled. All right, so Shannon left the science fair and traveled toward the recycling plant. Amanda left 1 hour later, traveling 22 miles per hour faster in an effort to catch up to her. After 2 hours of traveling, Amanda finally caught up. What was Shannon's average speed? Here's the key question here. What was Shannon's average speed? I can tell you this is kind of a difficult problem to solve if you've never done a motion word problem, right? You really have a lot of things that you have to consider here. So the first thing is, let's revisit our distance formula. So distance is equal to the rate of speed times the time traveled. And again, if you ever forget that, just think about, okay, I'm taking a road trip and I'm going for 2 hours, that's my time, times 50 miles per hour, that's my rate of speed, that gives me a distance. So in that case, 100 is equal to rate of speed of 50 times time traveled 2. And I left the units out just for simplicity, but this is 50 miles per hour, this is 2 hours, this is 100 miles. Now, you see that one side equals the other. So if I have a rate of speed and a time traveled, I have a distance, right? I can calculate that. Now, knowing this information here, if we go back up to the problem, kind of the first thing we're given is that Shannon left the science fair and traveled towards the recycling plant. It doesn't give us a distance. Amanda left 1 hour later, traveling 22 miles per hour faster in an effort to catch up to her. After 2 hours, so this is key, after 2 hours of traveling, Amanda finally caught up. So one thing we know about the distance, in this particular case, Amanda and Shannon travel the same amount, or travel the same distance. So their distances in the end will be equal. Now, later on in algebra, we use some different types of notation which won't come up for a while, but I'm going to write D, a capital D, with a small a to relate the amount of distance. This is the distance for Amanda. And this is equal to, I'm going to put a big D with a little s, and this is the distance for Shannon. And this is just here to show you that these two distances are equal. They both leave from the same place, and they both go to the same place. Now, they do it in a different amount of time, and so they do it at different rates as well. So the time is different, and the rate of speed is different, but the distances are the same. So that's the first thing. So let's talk a little bit about time now. So Shannon left the science fair and traveled toward the recycling plant. Amanda left 1 hour later. So whatever amount of time that Shannon drives for, it's an hour more than Amanda, because Amanda delayed her trip by an hour. So it says here, after 2 hours of traveling, Amanda finally caught up. If Amanda drives for 2 hours and she drove for an hour less than Shannon, then Shannon drove for 3 hours. So when we talk about time, let's put a big T and a little a, and this is the time for Amanda. Time for Amanda. Let's put a big T and a little s, and this is the time for Shannon. And we know the time for Amanda is 2 hours. We know the time for Shannon is 1 more hour than that, so 3 hours. So I just put 2 and then 3. Just need to get some information about the rate of speed. So Shannon left the science fair and traveled toward the recycling plant. Amanda left 1 hour later, traveling 22 miles per hour faster in an effort to catch up to her. Now, what I can do here, since Amanda is going 22 miles per hour faster, I don't know how fast Shannon's going. So I can use a variable to represent that. So let's let x equal Shannon's speed in miles per hour. So then, x plus 22, as it tells us in the problem, she's going 22 miles per hour faster, Amanda is going to equal Amanda's speed. Again, this is in miles per hour. So, we have a little bit more information. Let me scroll down and get a little room. We know from the distance formula, again, distance is equal to rate of speed times time traveled. So for Shannon, what information do we have? Her distance, we have her rate of speed, which I assigned the variable x to, and we have her time as 3 for 3 hours. So distance for her equals 3x. Now for Amanda, her distance looks like this. She has a time traveled of 2 hours, and her rate of speed is x plus 22. Remember, x plus 22 is the rate of speed, so the whole thing has to be multiplied by 2. If you don't use parentheses, this just looks like 2x plus 22. That's wrong. The 2 has to be multiplied by the entire thing, each term. So we have a distance for each person individually, and remember the two distances are the same. So this is how we get our equation in this type of problem. We know that Shannon's distance, okay, remember I put d with a little s for Shannon's distance, is equal to Amanda's distance, d with a little a. So I can take 3x, which relates to Shannon's distance, 3x, and I can set that equal to 2 times the quantity x plus 22. Remember, if you give me a rate times the time, I have a distance. So I have a rate times the time here, that's a distance, and it's equal to or the same as a rate times the time here, which is another distance, right? These two distances are the same. They look different because the time and the rates are different, but in the end they're the same. So what I can do now is just solve this equation and find out rates of speed. So over here I'm going to simplify. 2 times x is 2x, plus 2 times 22, that's 44. Over here I have 3x. Subtract 2x away from each side. Very, very simple equation. We end up with x is equal to 44. Remember, 44 was the rate of speed for Shannon. Let x equal Shannon's speed in miles per hour. Then x plus 22, or 44 plus 22, or 66, is Amanda's speed in miles per hour. So let's go ahead and write our answer. So what was Shannon's average speed is our official question. So Shannon's average speed was 44 miles per hour. And we can check this to make sure that it's true. So we know that Shannon traveled for 3 hours. So 3 hours, think about your road trip. 3 hours times 44 miles per hour. How far am I going to go? I'm going to go 132 miles. Now, we also know that Amanda leaves an hour after her, so she only travels for 2 hours. She's traveling at x plus 22 miles per hour. X was 44. 44 plus 22 is 66, so 2 times 66. She drives for 2 hours at 66 miles per hour. How far does she go? She goes 132 miles. Right? So these distances, again, are equal. And so we know we have the correct answer. Shannon's average speed here was 44 miles per hour.